Testing, 1, 2, 3. Okay, today we're going to enter into what amounts to the second phase of the course. We've considered many different topics so far, from the old history of mathematics to Mesopotamian Greek, up through the earliest axiomatic systems, and then on to the beginnings of analysis and limits, functions, the earliest aspects of geometry up through modern geometry, an extension of that into the calculus of variations, and then complex arithmetic. What I'd like to do today is to look at Lecture 19, which is an overview of, 10 problems that I more or less picked up at random, either because I knew something about them or was particularly interested in them. Now these are going to be suitable for your final project. Now, as far as the format for the final project goes, I'd like for you to essentially create an electronic document. It could be on the web, it could be a PDF file, TeX or Word, or it could be, don't make it handwritten and sent in by fax, that would not be good, but something that I can post. So it should involve a clear statement of the problem, one of the 10 or other problems that you might submit. It should contain a fairly extensive historical background. It should also list and describe some of the areas of mathematics which are impacted or defined by or involved with the problem and its solution methods. It should also give an indication of the key elements in the solution of the problem, if it in fact has a solution of the problem, or attempts at a solution or a proof of the theorem in the case of the n-body problem or Fermat's last theorem. And please do it in your own words. Don't just cut and paste stuff out of the web. That would not be the goal of this. Also, at the end, there should be additional material in the sense of a bibliography or reference list or a Maple, MATLAB code, etc. So I'll be a little more specific as the time goes on. So I've also indicated, in addition to the 10 projects here, I've given you more or less a starting point to launch your investigations into each of these areas. So I'll kind of go over these now, just to give an indication of their context and their importance. So the first one of the oldest ones in terms of problems, is in factoring numbers, or factoring not factoring primes, factoring numbers into primes is what I meant. So the idea is to consider this very old problem of factoring numbers, large integers into products of primes, and how this relates to modern encryption algorithms. For example, the RSA encryption algorithm, which I have a link to here, or the DES, MD5, all sorts of algorithms that do exist. One of the possibilities that you can do for this particular project is to write a Maple code or a MATLAB code to actually implement the RSA algorithm. It's not that horrendously difficult, and you could actually write a simple Maple program that will encode text and decode it with a key. So as a starting point for this, I think this is a reference actually that is contained in an earlier link. The RSA algorithm is the last names of Rivest, Shamir, and Edelman, RSA. The first and third people actually have a link. And this goes through the mathematics underlying the RSA public key encryption algorithm. And it just goes step by step. So you're trying to find two large prime numbers. And then you go through some additional steps just on divisibility, and then continuing on, here's an example of an encryption algorithm with a specific P, a Q, the product, E, and D, and this goes through step by step out of this. So this particular long number here is a large number modulo 133, so you can actually compute this number, which is 855 raised to the 2,753rd power, which is pretty large, modulo 3233. Okay, now there is actually, in terms of the implementation of this algorithm, here's the RSA algorithm in Perl in 2 lines. If you like dense one-line codes, this is about as dense as it gets. So this actually is a valid Perl statement. Perl stands for Practical Extraction Relationship Language or something. It's a language that's meant to handle string expressions, and each of these echoing and splitting and packing and popping and unpacking and all that stuff stands for various Perl or Unix commands. So this is a way to actually encode an expression into RSA in 2 lines. Now, granted, you're probably going to have a longer algorithm than this, or a longer code. Now, I should mention there are other, presumably more secure and more sophisticated encryption algorithms that are in use. Some of the early ones, like the DES. Many of these are available under Unix, and a lot of these are available under Windows. So by looking at the encryption algorithm, you can explain exactly how prime factorization enters into it, and more or less the security of the encryption algorithm is related to the cost of factorization of primes. If you have 512-digit or 1024-digit primes, those are fairly hard. Or if you give just a 1024-digit number, just to factor it into a prime is a fairly complex algorithm. Another sample problem has to do with chaos. Chaos is a much more contemporary mathematical subject. So one of the ideas you could do for this project is to look in the literature. For example, on the Lorentz attractor, this is a link that gives the history of the Lorentz attractor. It's a 3-dimensional nonlinear ordinary differential equation system. Now, it actually arises from a meteorological model, which is given here as a system of partial differential equations, nonlinear. There's all sorts of products and first derivatives and second derivatives. And this comes from hydrodynamics. But if you look for a periodic solution of this form for psi and theta, if you substitute it into there, you end up with a system of nonlinear differential equations here, known as the Lorentz equations. Now, these are just normalizations of the Reynolds number and Rayleigh numbers, etc., Prandtl numbers. These are critical numbers that describe the physics of the flow. Okay, and it gives some information here. Here's a picture of the Lorentz attractor in 3 dimensions. Since it's a 3-by-3 system, you're actually tracking a particle in x, y, and z. And notice this is a linear system here. This is nonlinear, this is nonlinear, and it comes in as product nonlinearities. Now, if you go ahead and launch this with given initial conditions, you get a picture that looks like this. Now, the importance of the Lorentz equations is that they are very sensitive to initial conditions. This is a hallmark of essentially chaotic or unstable physical processes. If you take the Lorentz attractor system and start it with arbitrarily close but different initial data, eventually the solutions will diverge apart from each other. In other words, solutions which remain close will not remain close forever. So it's not stable in that sense. Now, this was actually discovered by accident, as I think we might have mentioned before. Lorentz actually was running a very long run overnight. This was back probably in the 60s or so. For some reason, the run aborted at the middle of the night, and he wanted to restart it somewhere in the middle rather than at the beginning. So he just keyed in the last data, or sometime before it ended, and was going to restart, but then he noticed that just the round off that he did when he just gave 8 significant digits caused it to diverge very quickly from the last part of the run that he had a record of. And so this led him to suspect there was probably an error in the code, but after a lot of experimentation numerically, he discovered that that was an intrinsic part of the differential equation system, the instability. So this is a very nice kind of practical one. Fractals, iterated systems, there's some aspects you could launch into iterated function systems and data compression and things. Another example, more classical, is or historically older, is the geometry. So projective geometry is an aspect of modern geometry that influences computer graphics. So if you start off at this point, this is an introduction to projective geometry for computer vision. You can click, there's a PDF link, you can get the PostScript, or you can navigate it through HTML. It's not the world's best PDF file because the fonts are kind of funky, but it's nevertheless readable. Coming up shortly. Yeah. You wouldn't believe the amount of time I've spent today trying to get these fonts to look better. Because they're old Type 3 bitmap fonts rather than the PostScript embedded fonts that are scalable. So it looks pretty bad. Anyhow, not everybody has. If you have the tech file, you can rerun it, but it's not so easy to change PostScript Type 3 to Type 1 fonts. Algorithmic complexity theory is another example. We've talked about some very hard problems, hard in the sense of NP, the traveling salesman, and 4-color problems, graph coloring problems. Also, there's a link to Carmichael's algorithm. You can find that. This was what's called an interior point algorithm, which is a tremendous leap forward. So you can do a little bit of history on the mathematics. This is a very important aspect for computer science because algorithmic complexity essentially gives you the cost in terms of numbers of operations and asymptotics for how fast you can complete an algorithm. And so algorithms which are efficient in terms of a complexity tend to be the ones that are very much used. For after all, if you could shave 5% off of an algorithm and say calculated scheduling or something, you might be able to save quite a bit of money. Another more exotic topic for a final project would be infinitesimals. These were actually very early into the theory or the origins of the calculus. Back then they were known as fluxions. Now they've had a resurgence in modern times in non-standard analysis or transfinite mathematics, and there's a starting point here on non-standard analysis. A transfinite number is in fact a number which is larger than any other positive integer, or smaller than any other negative integer, but not exactly infinite. And an infinitesimal is like 1 over a transfinite number. Question? Okay, question was just asked whether each person in the class had to do a different project. The answer is no, because I'm not going to make 19 different projects. So you're allowed to you do the same project. So just ask that you do your own work and not collaborate on the final project. Another, in a sequence of links here, number 6 is non-Euclidean geometry for some of those who have more geometrical interests. So the project here is to find and develop at least one real-world application of non-Euclidean geometry. And I've seen in my travels on the web applications of hyperbolic geometry to database mining and graphical analysis of data and things like this, sort of defining the distance metrics in terms of closeness of data. So there's a lot of applications you can find, but you're supposed to, in your own words, give the explanation of the history, the importance, the techniques, etc. So there's an application starting point, launching point here for number 6. So this should be giving you a list of resources here for non-Euclidean geometry. So there's introductions and applications and theory and books, etc. So that's more or less a large list of references. A very famous problem in physics is the n-body problem, and I can actually sort of sketch out what that is. The n-body problem Okay, the n-body problem comes back from physics, where if you have n equals 2, if you have, say, a large mass and a small mass, think of this as the sun and the earth, separated by a distance r, the force between them is it's proportional to m1, m2, inversely proportional to the distance between them squared, and there's some universal constant called the universal gravitational constant that enters here. Now, if you actually look at the differential equations that govern these and just use the force, you can see that pretty much this will spiral and eventually they'll gradually attract each other. Since gravitation is universally attractive, if there's only two bodies, eventually they'll attract one another. Now, this could be small, but it is long range. Now, the gravitational force is long range and always, as far as we know, positive. So it's attractive, and we haven't found a anti-gravity yet, and it's long range. There are some actual cases in which there should be theoretically repulsive forces due to gravity, but there is some pretty exotic stuff in modern physics. Okay, so early on, people could actually solve the differential equations for n equal 2, so they said, well, let's just go ahead and put the sun and the moon and the earth and Mars and all these things and just stick it in and see what happens when we solve the equation. Okay, so if I have n equals 3, we now get to be very much more complicated. So n equals 3, suppose you have the sun, and then you have the earth, and then suppose you have the moon over here. So this rotates that, and then as a whole, this rotates the sun. Okay, so the question is can you solve the equations of motion? So you have a 3 by 3 system, and you can try to solve it. And the question is, are there any stable orbits? Are there any stable things where these things don't actually spiral in here? Can you find cases where this will orbit around and there will be what are called Lagrange equilibrium points? So it turned out that this was very, very hard, and that there was, in fact, no closed-form solutions. In fact, if you do this problem, you can do a historical search, and there was actually a prize offered back in the 1800s. Some very famous people like Poincaré worked on this, trying to find solutions of the n-body problem. Oops. So if you look on the web, you can find some links to the n-body problem. Here's a classic reference here. The one-body problem is just F equals ma. The two-body problem is just an attraction between two bodies, and that was solved by Isaac Newton. The three-body problem was so difficult even Newton couldn't solve it. And so they began working on it. So, for example, Laplace, shown here on the right, tried to solve, he solved a special case but fell at the general one. what you have is you have essentially forces between this particle and this particle. So if this is, say, M1, M2, M3, you would have that the mass M1 times its position of the center of gravity, say x1 double dot, would be equal to the applied force. So there would be a force on 1 due to 2, plus there's a force on 1 due to 3. And say F I comma j is G mi mj over rij squared. So you can actually put this in here and you get a system. And in fact, it looks like the force on mi xi double dot as a vector is going to be equal to the force of I, j, the sum of them, where of course j does not equal I. The reason why, of course, you don't include j equals I is a body does not exert force on itself. There is no self-induced gravitational forces. If you have a planet all by itself in the universe, the planet cannot cause itself to move, so you don't allow that. So, and then of course you're giving x at the initial time, x sub I, and you're given xi dot at initial time for all I, and then you just have to solve. Yeah, the planets actually, we'll assume that these are basically homogeneous, although that's not really the complicating issue. The structure of the planet inside does or doesn't, because if you have basically a given mass at a given center of gravity, the gravitational force is the same, regardless of its internal structure. It's only when you're inside that you have to start feeling some of the effects of the internal. Okay. So this is the story of the n-body problem. Those of you who are more applied and interest can go look at that. Another very classical problem is the non-solvability of quintic polynomials with degree 5 or more. Since it actually turns out that you have the quadratic formula, which we all know, ax squared plus bx plus c equals 0, you can write down minus b plus or minus. And then you might have ax cubed plus bx squared plus cx plus d. There's an actual analogous formula, and there's one for even fourth order. In terms of the coefficients, but for, so n equals 4, n equals 3, n equals 2, n equals 1 is pretty easy. N equals 5, there's no closed form expression for the roots of a fifth order polynomial in terms of its coefficients, other than very special cases. Okay, and this has to do with some fairly deep results in algebra, so if you want to begin there, this is an example of the impossibility of solving general quintics in terms of radicals, so they're not constructible. Okay. Two other links, this one's more or less applied. Fractals and fractional dimensions explore the relationships between Mandelbrot and Julia sets, as well as Feigenbaum's universal constant. Now, for those of you who don't know what Feigenbaum's universal constant is, that's a very amazing number. Oops, that's not actually in this reference. Let me get a link to it. Testing. Now, Feigenbaum's universal constants are a very fascinating subject, because they truly are universal. They govern some behavior related to what's called period doubling. Now, period doubling has to do with this, you might recognize as a bifurcation diagram. So what this says is that for a given value of mu, you have a specific frequency of the final solution. When you get to a critical number, somewhere down in here, you get a choice of two frequencies. Now each of those two then, at some special number down here, splits into two, so now you have 4. And if you were to blow this region up, this 4 would split into 8. So you have one frequency splitting into 2, splitting into 4, splitting into 8. Eventually it splits and splits and splits in this very complicated path here. Now if you actually look at the frequencies, you have an iterated function map, so 1 minus mu x to raised to the r power. If you look at that, it has frequencies that look like this. Now, if you look at the relative ratios, this constant n, delta, is known as the Feigenbaum constant. If you solve for it and you take a certain limit, for the logistic equation, you get a characteristic set of numbers. And what Feigenbaum did was actually look at this analysis for various iterated functions that came up in not just logistics, but other systems like chemical systems or vibrational systems. And he found these same constants appearing. And so he suspected there was some universal law that governed the approach to, in the neighborhood of the periodic doubling. And that's in fact the case as long as certain numbers or certain values are positive or negative or bounded in some interval, you can show that these constants are in fact universal and can be explicitly computed. So that's a very fascinating area of mathematics, applied mathematics, relating fractional dimensions, these Hausdorff dimensions that we've talked about, and I'll leave you to look up the relationship, what the definition of Mandelbrot and Julia sets, as well as how they relate to periodic doubling, the onset of chaos, turbulence, etc. So this is actually related to topic number 2. Okay, the final 10th topic here that I picked up is a very famous one. We've talked about it before, Fermat's last theorem, and this project will involve exploring the history of this problem from the various earlier stages, namely finding Pythagorean triples. And you'll remember what a Pythagorean triple is. A Pythagorean triple is just a set of numbers A, B, and C that are related by being sides of a right triangle. So A, B, and C are integers. And if you set n equals 2 here, if the general case, a to the n plus b to the n equals c to the n, the question is, does this have integer solutions for n bigger than 2? And this is, of course, the subject of Fermat's last theorem. The statement was that it doesn't. So the history of this is long and rich, and people have tried. Fermat has a very famous comment that you probably remember about discovering a truly marvelous proof of the result, but not being able to fit it on the little scrap of paper that he was writing it down on. And some people have a little bit of doubts, considering that the shortest proof now is several hundred pages long. I think the original one was 600 pages long, whether in fact he could have squeezed that onto a back of a postcard or envelope or whatever he had. So the starting point here is just a general survey article on Fermat's last theorem. So there's history and various things. So again, the idea is to choose one of these 10 topics or suggest your own and look at the format namely give a clear statement of the problem, explain clearly what it is that you're going to be describing, go through as extensive a historical background as you have time to do. Now, we have almost a month to work on this, so I expect to assist you if you get stuck or interact with you if you have questions on what you're going to be doing. Please list the areas of mathematics that were impacted by the problem or the solution methods, and in your own words, summarize the key elements that are involved, mathematically speaking, in the solution of the problem and how it's impacted, say, modern areas of mathematics or other science. And if you have any additional material, such as an exhaustive list of links or things, the format is either a website, if you have access to creating a website, or an electronic form of document, Word, text, PDF, PostScript, whatever.